Hello, everybody. This is Group 6, and this is our final project on image similarity using CLIP and ResNet. This is by Jet, Justin, Alex, and Pepper. So now I'm going to go into our learning task. So for our learning task, it was to measure how similar two images are. We used the tiny ImageNet dataset and trained two models, CLIP and ResNet, to learn this task. Then, using the testing set, we compared pairs of images to see how well each model judged similarity.
Hello everyone, my name is Pepper, and I'll be going over the models we decided to use. Our first model was ResNet. So the convolutional neural networks that we discussed in class are known to perform better with more layers. However, training deep CNNs is very slow and very costly. On top of this, they're vulnerable to the vanishing or exploding gradient problem. This is where the weights on the model gets either so small or so big that the model can't effectively update and the whole thing breaks. ResNet was designed as a solution to this problem. Layers are taken in as residual functions with reference to layer inputs. So we can see the structure over here. Basically, the input x comes in through here, goes through the weight layers, and becomes f of x, and then is added back in later at another layer to get f of x plus x, and that is our residual function. This allows for the faster training of more accurate and deeper models. So here we can see a traditional CNN here, and the ResNet CNN here. And as you can see, the ResNet converges much faster and has a better end result with lower error. So the original implementation in the paper was ResNet 34. However, our implementation, we chose to do ResNet 50. There are 50 total layers, 48 convolutional layers, 1 max pool, and 1 average pool layer. Layers are stacked in sets of 3s instead of 2s, and there are bottlenecks in between, which are these little 1 by 1 layers that help produce the matrix calculations that we need to perform. So here we see the ResNet structure here with the 1 by 1, the 3 by 3, and the 1 by 1. For our second model, we chose CLIP. So most machine learning algorithms can only take in images with a single descriptor and can decide between a fixed set of options. For example, if you were to train a model based on images of cats and dogs, it could only differentiate between cats and dogs. It could not differentiate, say, with what this is. It would think it's either a cat or a dog. What if there was a way to understand the relationship between text and images? This is what CLIP is for. CLIP takes in both images and descriptive tags and relates them to each other, and can be trained on new topics without retraining the whole model. And this is very big because retraining models is very expensive. So the first step here, it takes in the image and its label, encodes them both, and puts them together in a matrix. Then it creates a dataset classifier from the label text, and you can just add these in, they're all stored. And then it uses that to predict what the image is going to be based on the relational matrix. For our implementation of CLIP, we used a vision transformer. So there are also ResNet-based implementations of CLIP, but we already did ResNet, so we're going to use the transformer instead. So the transformer is also used for text, and this is very good for CLIP because it can be used for both parts. So here we see the basic workings of the CLIP transformer. Basically, we have the positional encoding here. It becomes a vector. It's fed into here with the positional encoding for context. And it's fed into the transformer, into the head, and we get our logits.
Hi, my name is Justin, and I'm going to be talking about our data and our pre-processing. So for our data, we use the tiny ImageNet dataset. It has 200 different object classes and is downsized to 64 by 64 pixels so that the data is more lightweight and trains faster, while still preserving enough data for classification. The dataset comes with these predefined dataset splits. So it comes with the training, so 500 training images, 50 validation images, and 50 test images per class. And using these splits ensure that every model we train get the same training and evaluation layout and keeps the results consistent. for the pre-processing for our ResNet, because ResNet has like a specific 224 by 224 format, we first resized the image to 256 by 256 to get consistent input sizes. Then we cropped it back down to 224 by 224. And then we converted the PIL image to the PyTorch tensor so that the model can process it. Finally, we normalized the pixel values using the same mean and standard deviation that ImageNet uses, and it would keep our data distribution consistent with what ResNet expects. Our custom collab function batches all of those pre-processed images and labels them together so training runs efficiently. For clip, it's slightly similar in terms of the size and the collab function, but there's like a little difference. And for the clip, we used Clip's built-in pre-processing pipeline. It automatically resizes the tiny ImageNet images and then centers it. And then before pre-processing, all images are also converted to RGB so that the inputs stay consistent with how Clip was originally trained. The pipeline also applies clip-specific normalization values to match the model's expected input distribution. After that, the images are converted into tensors, and then the custom collab function would handle the batching, and then the data is then packaged correctly for training. And that's it for the data and pre-processing.
Hi, this is Jet, and I'll be going over our group's hyperparameter tuning. For our first tuning, we use learning rate scheduling for both ResNet and Clip. For learning rate scheduling, we tuned the learning rate strategy by introducing a reduce LR on plateau scheduler, adjusting reduction factor to 0.25, meaning the learning rate reduces by a factor of 0.25 when progress stalls. This was done to control how aggressively the learning rate decreases when validation accuracy stalls. This tuning allowed the classifier head to take larger steps early in training and progressively finer steps near convergence. As a result, the optimization became more stable and avoided the accuracy plateau caused by a static learning rate. We also use regularization settings, but only for Clip. We tuned regularization hyperparameters to improve generalization using label smoothing and mix-up augmentation. Label smoothing slightly softens the target labels during training. For example, instead of treating the correct class as a hard 1 and all others as 0, as we normally do, it assigns something like 0.9 to the correct class and distributes 0.1 across the others. This prevents the model from becoming overly confident and improves generalization. And now for mix-up augmentation, it creates new training examples by blending two images together and mixing their labels in the same proportion. This forces the model to learn smoother decision boundaries and reduces overfitting because it sees a wider variety of input combinations than in the original dataset. As we can see here in the mix-up example, we mix the cat and dog images to create a cat-dog mix-up. These choices helped reduce overfitting while keeping training stable. Together with architectural stabilizers like layer norm and GELU, these techniques enabled the classifier to learn more robust features from tiny ImageNet.
Now we're going to be going over the graphs and analysis. We trained our models over 10 epochs, and the accuracy steadily increased over time. The accuracies for ResNet increased steeper in the first half of training and leveled out on the second half, reaching almost 100% accuracy. Clip, on the other hand, had more of a steady increase in accuracy throughout the entire duration of training, reaching about 80% accuracy by the last epoch. The validation sets showed significant fluctuations on ResNet and a smoother transition on Clip. At around epochs 4 and 5, ResNet hit a plateau on accuracy, so the learning rate was modified, and the plateau was overcome. Label smoothing and mix-up augmentation was made for Clip's classifier head, and it generalized better, and it kept validation accuracy improving, so it never flattened early like ResNet did. To analyze whether images were similar in the test set, we implemented this formula for each batch. The basic idea for our approach was taking all of the pairs that initially had the same class and comparing them to the predicted classes for the same image set. If the predicted and actual image class pairs matched, we would add 1 to the correct tally. Otherwise, we would add a 0. Once all of the image pairs in that batch were processed, we would divide that by the number of pairs in the ground truth set that have matching classes, and then we would achieve the accuracy for that batch. For performance, since we were now evaluating the accuracy by a different method, the percentages did go down overall. However, our evaluations showed that both methods performed similarly despite the large differences in training accuracies. In relation to the performance of the ResNet model, our implementation of CLIP performed better, with less of a decrease in accuracy between the training and testing sets. The extensive hyperparameter tuning that we implemented for CLIP to avoid overfitting our data was the reason that this accuracy decreased less than the ResNet, and we avoided overfitting our data in that way. If more epochs were performed, we hypothesized that CLIP would perform better than ResNet due to the overfitting precautions that we created. Here are our sources. Thank you.